For this problem it says, on a compound microscope the focal length of the object is 3.50 centimeters and that of the eyepiece is 6.50 centimeters. The distance between the lenses is 26.0 centimeters, so I'm just going to write this on here. So here is L equals 26.0 centimeters, and the focal length of the eyepiece here is 6.50 centimeters, and the focal length of the objective lens is 3.50 centimeters. What is the angle of magnification of the microscope if the person using it has a near point of 35.0 centimeters? I'm just going to look up what kind of symbol they use for the near point. Capital N equals 20, what was it again, 35.0 centimeters. If, as usual, the first image lies just inside the focal point of the eyepiece, how far is the object from the objective? So what it says is, how far is the object here from the objective? We have to figure that out. It's going to be pretty close to the objective focal length, so relatively close to 3.50 centimeters. What is the magnification, not the angle of magnification, of the objective? Okay, so I'm going to use the magnification. I'm sorry, hold on. Yeah, I'm going to use the angle of magnification equation for the microscope, which says m equals negative L minus Fe times the near point divided by the two focal lengths. Come up with something. No units, because this one is a ratio. This one is larger than this one here, so that's positive, that's positive, all of these are positive. We will come up with a negative magnification, which simply means that the image is turned around from the object. Plugging in numbers. There we go. Kind of, oops. Inside here, I don't even know if I can, trying to squeeze this in here. There, try it again. There we go, I think that's okay. Alright, so it's going to be a negative parentheses, and what is this, 26 minus 6.5 parentheses times 35 divided by 3.5 times 6.5. There we go. Enter, and I come up with an angle of magnification of negative 30. Again, a negative meaning that it's turned around. Then use the thin lens equation. So it's going to be 1 over FO in this case equals 1 over DO plus 1 over DI. Okay. That one, of course, is this one here. The DO is what we're supposed to figure out. And the DI is actually not very well explained, I believe, in the book. So I got this part here from hyperphysics. And yes, in the book they have a similar drawing, but the detail is not quite the same. They do mention that the image is at infinity. That means the image, that is being produced here um, from the objective lens, and that then gets here. Right here is the image distance, which is the focal length. That's actually the blurry point, and here the if you go through the thin lens equation here, and if this one here is the new object distance, which equals then the focal length, you come up with an image distance of infinity, because 1 over one number, the focal length in this case 6.5 centimeters, minus 1 over the object distance, also being 6.5 centimeters, comes out to 0. And the only way it can achieve that with a reciprocal is if you divide 1 by infinity. In any case, the image distance here from the objective lens is therefore going to be the total length, the total distance between the two, minus the focal length of the eyepiece. And that's the point that they didn't make quite in the book. So this one is also L minus FE, which comes out to, let's see, 19.5 centimeters, right? So this one here is then the object distance. This one here is the image distance from here to here. Looks a little bit far out, maybe it's somewhere here. That's the 6.5 centimeters, and then this here would be the 19.5 centimeters. And the focal length, of course, is this one. And again, plugging it into the calculator is going to give, let's see, 1 over 3.5. And then it's going to be minus 1 over 19.5, and then take the inverse to get the DO, the object distance, and that's going to be 4.27 centimeters. So this distance here is 4.27 centimeters. Oops, I didn't mean to write this down actually. Just DO equals that. Okay, and then it says, what is the magnification of just the objective lens? And of course that's going to be M equals negative DI over DO, and again that's going to be a ratio, no units. The DI here is the 19.5 centimeters, the DO is the 4.27 centimeters that was just calculated, and when you plug these in, you're going to come up with roughly negative 4.5 as the ratio for the magnification of just the objective lens. This is a problem for the Lensmaker equation, and it's not in the book. I made it up. So some books cover it, some other introductory physics book decide that it's just a little bit too much. They have to cover a lot of optics, so Lensman Equation is sometimes something they leave out. I want to mention it because in order to get spectacles, that is eyeglasses, there has to be somebody who is manufacturing them, and they have to do it just right so that the vision is corrected. I have pretty bad eyes. That means I need really quite corrective eyeglasses. My far point is only about 12 centimeters, that is about 5 inches away from my eye. That means without corrective eyeglasses or contact lenses, I can only see to about 5 inches, and beyond that things become blurry. as far as the far point is concerned, when I put eyeglasses here, that far point is supposed to be removed, the image point here, to look at objects that are as far as infinity away. So DO, I want to look at objects that are at infinity, because then with my corrective eyeglasses I can cross the street, I can drive a car, and so on. Okay, so that means what's the focal length of these eyeglasses that I need? Well, I'm going to use the thin lens equation, which is 1 over f over 1 over do plus 1 over di. And this one here would be infinity, and this one here would be, since that far away object out here needs to be moved to my far point, the image distance, which would be a virtual image, that here would be the 12 centimeters minus the 2 centimeters where the lens is. And I should perhaps move that a little bit over here. Well, yeah, it doesn't show quite right. So, okay, let's make it 11 centimeters. 1 centimeter. So 10 minus 12 minus 1 centimeter. So 12 minus 1 centimeters, and since it's a virtual image, that needs to be a negative. And then what you see here with this particular fraction, 1 divided by infinity, is virtually 0, and that means it's pretty much 1 over f equals 1 over di, which means the focal length is the same as the image distance. So it follows that the focal length that my corrective eyeglasses would need would have to be negative 11 centimeters, which is in diopters negative 9, because diopters are computed as 100 divided by the focal length. So my optometrist would have to assign me negative 9.00 diopters, and that's about right. That's what I get. Okay, but that still means that the lens maker has to manufacture the lens, and they would have to pay attention to make this side of the eyeglasses to be concave and this side here to be convex, and the concave side has to be stronger. That means has to have a smaller radius in order to make an overall concave lens, because that's what I need. I need a negative focal length. Respectively, it's called meniscus concave lens. Okay, this is the Lensmaker equation. Looks quite complicated. Here's the radius of the curvature of the lens closest to the light source, and then there's the radius the other one, and then here's the index of refraction of the lens material that is being used, and then this is the resulting focal length. This here would be the thickness of the lens. Here it comes. This is kind of like yet another corrective term. Let's make life a little bit easier. This one here, let's see, is it this one? Yep, this is at hyperphysics. There's again the lens maker's formula, and P lens here, yeah, that would be in diopters respectively 1 over f. Almost looks like kind of the thin lens equation with this one over here, and so on. Unfortunately, I already put the numbers in here that I wanted to put in there, and now it's just assigning itself numbers. So well, in any case, what I have done with my eyeglasses at home, I looked at this side here, the convex side, and I decided it's so flat that I would call its radius to be infinity. I know this looks weird. I wrote on the same page twice equals infinity. You can't really do that mathematically. It should be like proportional to infinity or a really large number. And the radius of the concave side, for that what I did is with my real glasses I put a caliper here, and then I kind of put a caliper on the side here to figure out what this one is in the middle. And so I had these two measurements, and I had this distance here that would be called the chord, and from that I made, let's see, I made a calculation using circular segments. And so I measured this one here, and I measured the thickness of that curvature, and I figured out what the radius was, and that was a kind of like a rough measurement. I came up with 7.5 centimeters. That's rounded to the closest half centimeter. Okay, then I used the Lensman equation, which says 1 over f equals n minus 1. You saw it a moment ago on both Wikipedia and Hyperphysics. So index of refraction minus 1 times 1 over r1 minus 1 over r2. The sign convention for the two curvature is, imagine you have a convex lens with the same radius, then one of the radius has to be positive and the other radius needs to be negative, because otherwise if it wasn't, then this would come out to 0 and the lens wouldn't have any focal length. So if the other side has a convex side as well, then that convex one would have to be negative. In any case, what I do have is I have a concave side, and that will make this one here positive. So this one here would be a 7.5 centimeter, and this one here would be kind of infinity, and this one here would be the index of refraction there. I don't know what I got. I assume that mine might be pretty strong and use flint glass that was talked about in a different problem, 1.67. And then I go to the calculator and I plug things in. So that would be parentheses 1.67 minus 1, index of refraction minus 1, times parentheses 1 divided by a very large number, let's say divided by 11,000 or 111,000, okay, minus, oops, I don't need that parentheses, 1 divided by 7.5, the one that I measured and calculated, close parentheses, close another parentheses, invert again in order to get the focal length, and I come up with negative 11 rounded, which compares negative 9 to negative 9 quite favorably. Oh, I'm sorry, here it is. Actually, here it is, negative 11, right on. Actually, of course, this one is includes the measurement errors that I had. I wasn't able to be totally accurate on when I used the caliper and my own glasses. So if I go, for example, here to Hyperphysics, if I plug this one in to be 1.67, and this one over here, yeah, a very large number, and this one here would be positive 7.5 for the concave radius that is considered to be positive. They mention that here as well. The radius R2 is negative if it's convex, but it's concave, so it must be positive. And I click somewhere else, and there I come up with the same thing, negative 11 centimeters for the focal length and negative 8 diopters, because this number is divided into 100. And that's what the lens maker would have to manufacture a lens according to these measurements, make it flat on one side, use a curvature of negative 7.5 centimeter radius on the other side, use flint glass 1.67, and that would give me the desired negative 11 centimeters for the focal length, which then makes sure that an object that is far out is moved towards my normal far point, my image point.